So here is one definition. It says that a mode is essentially a name given to a solution of the transverse field, both E and H, right? And because there is a transverse resonance condition, we call this a pattern, right? You actually get a transverse field pattern, similar to when we said that there is a standing wave pattern on transmission lines. We call this transverse field pattern. Remember, this field pattern, because of the resonance condition, does not quite alter as we move along the waveguide, right? Whose amplitude and polarization remain constant along the direction of propagation. Okay, so it's a transverse field pattern whose amplitude and polarization remain constant along the direction of propagation. This is sort of like a definition for mode, but we'll try to uncover and peel a little bit more, right? Because this looks very bookish, right? So we say that we have identified, right, a mode, right? So remember, a little bit of what we have done before this juncture is to try and gather some clues or perhaps some recipes in order to tease out the electric and magnetic field solutions without having to solve the Maxwell's equations, right? So we can say that the recipe or clue to finding this transverse field pattern is to try and satisfy a transverse resonance condition, right? So a guided mode, right? The reason I call it guided is a very natural question that students ask, right? I said the thetas are discretized for the parallel plate waveguide, and these specific angles gives rise to a transverse resonance condition, right? The question that arises next is, what if I move away from the theta and launch a plane wave, right? So you'll notice that if you did that, right, that subsequent reflections, the planes of constant phase would sort of not line up, right? And that you will basically at the end of multiple reflections just see that the electric and magnetic field dies down, right? So you cannot just launch at any arbitrary angle. So a guided mode can exist only when a transverse resonance Okay, so I've just written it down in sentence what we discussed earlier, right? So when this transverse resonance condition is satisfied, right, we notice that subsequent reflected plane waves all add up constructively, right, so as to maintain this transverse field pattern all along the propagation direction. Okay, but at this point I still find some students who are not quite happy with the definition of mode. This is what it is, but perhaps rather than looking at it as how do we best represent or how do we best describe what a mode is, I believe what is more important to realize is what is the use of modes. Right? Why are we in the hunt for finding these solutions? Why are we in the hunt so desperately to find these so called modes? Right? So, that is a very key important point. Right? So, remember that the unbounded situation, right? Maxwell's equations said that plane waves form our basis set, right, and that I can use many of such plane waves to construct complex electric magnetic field patterns, right. So we have moved there from there to actually using two sets of plane waves, right, to try and mimic the electric and magnetic field values without violating the boundary conditions, even in the bounded uh, region between the conducting plates, right. So it is clear from this that Maxwell's equations does not allow us to use plane wave solutions in bounded situations, right. A plane wave is no longer, with its infinite transverse extent, uh, cannot fit in this bounded media, right. So I cannot have my solutions for electric and magnetic fields in terms of sums of plane waves, right. So instead we actually have a different set of bases for the waveguides, and those are these modes, right. So the first thing that modes are useful for is the modes form an orthonormal set. Okay, so rather than using summations of plane waves to give me the net electric and magnetic fields in a new situation or a new scenario, I'm actually going to use modes as the means to express the net electric and magnetic fields, right, within the waveguide. Again, orthogonality in electromagnetism is very different from in linear algebra or vector algebra, right. So where there is a notion of perpendicularity, where vectors are perpendicular to each other. We discussed this at the time we were talking about polarization, right. So in the case of this definition, this mathematically equates to calculating the Pointing vector using the electric field of one mode and the magnetic field of another mode, right. Okay, this is a huge benefit, okay, which is to say that if I wanted to know what is the net power of all the electromagnetic fields that is within the parallel plate waveguide, right, I just have to simply find out the power in each mode, right, and I can just do a linear sum of all these powers, right. So the second thing is, if we look at mode I, just the electric field, right, from mode I and mode J, and integrate it over the cross section of the waveguide, I notice that this is also 0. if I not equal to j. Right. So there's another way to write this. So if the electric fields are normalized, we can actually say that this is delta ij. Right. The Kronecker delta function takes the value of 1 when I equals j and 0 when I not equal to j. Right. So this is to say that modes form a complete set okay right. There can exist no fields inside the parallel plate waveguide, right, that I cannot describe by a linear weighted combination of the field patterns from the individual modes that are supported in the waveguide. Okay, this is a very powerful statement, right? So one, these modes are orthogonal to each other, which means that the powers carried by each of them remain in these modes as we propagate along the waveguide, right? So there is no exchange of power between these modes. Very strong statement, right? Second, there can be no situation or scenario where the electric field and magnetic field inside a parallel plate waveguide cannot be described, right, by doing a linear summation of all the supported modes within the parallel plate waveguide, right. So this is what we call a modal expansion. So E net can be written as a weighted sum over all the modes, right. I should say all supported modes. Okay, so we call this modal expansion. Okay, so any arbitrary field can be expressed as a superposition, right. Superposition is just a fancy word of saying that a linear combination, right, a linear weighted combination of modes. Okay, so in my opinion, rather than trying to get into the minutiae of trying to perfectly describe what a mode is, I think it's more important to realize the importance of why mode solutions are important for the case of waveguides, right. So even though we are talking about parallel plate waveguides now, all these uh, conditions that we are talking about is true for any waveguiding structure, right. So we'll move from here to a very specific example of, say, a rectangular waveguide with perfect conductors in uh, two two axes, right, and the third axis is the direction of propagation. But this commonality of modes, right, is true across any waveguiding geometry. Okay, so remember that it is critical that the that we understand that we are after these modes for a very specific reason, right. They kind of form the basis set, right. Just like in the unbounded media, plane waves form a basis set for expressing electric and magnetic fields of any kind, right. Um, in the case of waveguides, there is a narrower domain or a narrower set of so-called modes, okay, that can be used to represent any kind of field that may be supported within the waveguide.